Welcome to Chapter 12, number 25. In Chapter 12, number 25, what we have here is we have a wheel, and what we're going to do is we're going to try to apply a force. We're going to try to apply a force here at the center axle in this direction here, and try to get this wheel entire to kind of go up over this stair here. And so the question is, given this scenario where the radius is 6 centimeters and the mass of the wheel is 0.8 kilograms, how much force would I have to apply to get this to go? So the wheel is a rigid object that's free to rotate. So what I'm going to do is I'm going to draw the wheel. I'm going to draw all the forces on it and see which of these apply some torques. And then we're going to decide balance forces, balance torques, and see if we can't write some net torque statements and go from there. So the first force I have here is I have the weight. So the earth is pulling it down. It pulls at the center of mass. I'm feeling pretty good about that. I also know that there's a applied force here. I'm feeling pretty good about that. But I gotta decide where the pivot point is. Is the easiest thing to do to make the pivot point at the center of mass? Or is it easier to make the pivot point someplace else? For this problem, it's easiest to make the pivot point right here at the place where it's actually going to pivot. So we're going to put the pivot point right there. It's going to lead us to a little bit of a geometry problem, not an issue. So what we have here is, and in the drawing, it says that the wheel has a radius of 6 centimeters, and then this stair lip here is 3 centimeters tall. So half the distance here, okay, we'll put it right here. So this is going to have a normal force here, okay? This is going to have a normal force here, and it's going to push in this direction. Now, I don't know how big to make it. We could figure that out later. It doesn't matter how big I'm making it because it's not going to supply a torque anyway because the radius is 0. So this is the pivot point right here. So I have these forces. Now, you may be asking yourself, what about the normal force that exists right here between the ground and the wheel? That's a great question. Normally you would put it there and it would be pointing up, but this is the thing that's very cool about this, is that in order to get this to go, I'm applying a force like this, it's rotating here, and when this normal force right here goes to 0, that's when it's going to rotate. And so that's a thing that we need to know. So the normal force with the ground is equal to 0, and this is our minimum condition. So it says, what is the minimum force I need? Well, I need just enough force so that the normal with the ground goes to 0. And using this idea, I can use the net force statements and the net torque statements, and I can go from there. So let's do a net torque statement and see what it looks like. Here's my pivot point. I'm going to need a different color for sure. So here's my pivot point. If I look at the torques, it's not rotating yet. The net torque is 0. What are the torques? Well, is this force supplying a torque? It absolutely is, right? So if this is my pivot point, my R vector, this is where the forces are being applied. So my R vector would be here. That's my R vector. So it's R times F times the sine of the angle between them, which would be this angle right here. We'll call it theta. So that's going to get it to rotate, well, it's going to get it to rotate this way. Well, this one would be negative. And what about the weight? Plus R mg times the sine of, well, if this one is theta, what is this one then? This one's got to be phi, where theta and phi are complementary. And those are the only two forces, and they both supply torques. Again, there's no normal force here. And I look over here, there's nothing else pulling or pushing. So it turns out that RF sine theta is equal to RMG sine phi. So we're going to be solving for the minimum force that I need. So the R, you can divide R out. So I have mg sine phi divided by sine theta. Let's look at these angles here. Okay, let's look at these angles and see if we can't figure them out. This is the hidden geometry problem. Okay, let's look for the hidden geometry problem. If I look over here, it says that this is 3 centimeters tall, which means this is 3 centimeters. And if this is 3 and the whole thing is 6, this is another 3, but the radius is 6. And so it looks like I have a triangle. I'll redraw it over here. Where this is 3 and this is 6. And it'd be really helpful if I knew this angle. For example, this one is theta. And this one is theta 2, and we call it theta there. So this is a relationship we actually know, where the shortest side of a triangle is 3 and the largest side of a triangle is... The shortest side of a triangle is 3 and the largest side of the triangle is 6. That's twice as much. That gives an indication right away that theta is equal to 30 degrees, which means that phi must be equal to 60 degrees. So let's plug and chug this here. I'm going to move this up. F is equal to, our mass is 0.8 kilograms. We're going to use 10 as our G value. Sine of 60 divided by sine 30. And it turns out that the minimum amount of force, again, I'm going to use 10 is my gravitational field strength, and I got 13.85 newtons. So this one was hard because there was a hidden geometry problem in here to figure out what the angles were, and you had to know that the normal at the ground went to 0 at the minimum force.